Assalamu alaikum. Here I am Jahangir Alam, lecturer in physics at Milestone College. I welcome you all in my online class. First of all, thanks to Almighty that He has given me the ability to take this class, and I am still okay and carrying on my regular activities. Dear students, I also hope all of you are well with your family members by the mercy of Almighty and carrying on your regular studies, staying at home. Right. Dear student, today we are going to discuss a very important topic from the first chapter of physics second paper. Dear student, right? I hope you got it. Today mainly we will discuss on entropy, change of entropy in reversible and irreversible processes, and some important mathematical problem related to our today's topic. Okay, dear student, so let's start our class. Dear student, now and first we have to know what entropy is. I think it is totally a new term in our physics, entropy. At first we can realize a situation. Suppose we are going to apply some amount of heat to a gaseous medium, right? So after the application of heat, you can feel that the molecule of the gas particle will be disordered, right? It will move randomly. So order of the gas molecule will be destroyed after the application of heat. That is, the disorderliness of the system will be increased, or the gas molecule will be moved in randomly, right? So a thermal state will be changed after the application of heat. So this property or thermal property which changes due to the application of heat is called entropy. That is, the disorderliness or randomness or haphazardness which will be increased by the application of heat is known as entropy. Right, dear student? I hope you got it. So now we can give the definition of entropy. The definition of entropy can be stated as the thermal property of a system which remains constant in adiabatic process or adiabatic change is called entropy. Entropy means the disorderliness of a system, right? Dear student, the entropy of a system cannot be measured or calculated, right? But we can calculate the change of entropy. So the change of entropy, entropy is denoted by S, and change of entropy, that is change of entropy will be denoted by del S. Del S can be expressed as del Q divided by T, right? So change of entropy can be stated as the rate of change of absorbed heat or rejected heat with respect to temperature of the system, right? So dear student, we can say change of entropy is stated as the rate of change of absorbed or rejected heat with respect to temperature of the system. Del S, this is the change of entropy, will be positive when the system absorb heat, and on the contrary, del S or the change of entropy will be negative when the system radiated heats, right? Dear student, I hope you got it. This is a very important definition for your exam. Dear student, now we will see the change of entropy in a reversible process, right? You know, the best example of reversible process is the Carnot cycle, right? Here we show graphically a Carnot cycle. In the Carnot cycle, you know, there are two expansion. One is isothermal expansion and second one is adiabatic expansion. And there are two compression. One is isothermal compression and another is adiabatic compression, right? If we represent when the gases expanded from A to B, this is called isothermal expansion. Here the temperature remains same at T1 degree Celsius or T1 degree Kelvin, absorbing heat Q1, right? So in this case, the system absorbing heat Q1 at temperature T1. So change of entropy will be take place in that case, right? And in the second expansion, then, that is when the gas was expanded adiabatically, no amount of heat will be absorbed or radiated. So in this sense, that is the change represented by B to C, there will be no change of entropy because the amount of heat will be 0 at the change. And in the third step, the gas will be compressed isothermally, that is the gas will be compressed from C to D, that volume will compress from C to D, and in that case the system will reject Q2 amount of heat at temperature T2. So another change of entropy will be take place in this state. And finally, when the gas was compressed adiabatically, that is in that case no amount of heat will be rejected or no amount of heat will be absorbed by the system. So no change of entropy will be takes place in the fourth step. So in the total cycle, in 2 step, change of entropy will be take place, and another 2 step there will be no change of entropy. That is in isothermal expansion and isothermal compression, change of entropy will be observed, and in adiabatic expansion and adiabatic compression no change of entropy will be observed, right? So dear student, for the total change or total cycle, if we calculate the change of entropy, we can calculate like that: change of entropy in isothermal expansion, right? If the change is denoted by del S AB, AB means the change represented by AB curve. So here the change will be denoted by plus Q1 by T1, because in this case the system absorb heat, so change of entropy will be positive, right? And change of entropy in BC expansion in adiabatic expansion, which can be expressed as del S BC is equal to 0, because there is no exchange of heat. Finally, the change of entropy in isothermal compression in isothermal compression, which is denoted by del S CD, it will be minus Q2 divided by T2, because in that stage the system will reject heat, so so change of entropy will be negative. And finally, the change of entropy in adiabatic compression, del S dA will be also 0. So total change of entropy, del S is equal to plus Q1 by T1 minus Q2 by T2. But dear student, you know, in case of Carnot cycle, a reversible process, we know Q1 by T1 is equal to Q2 by T2. That is, the ratio of Q and T will be same in case of reversible process or Carnot cycle. So from the expression we can say that del S will be 0. So, from the calculation or conclusion, we can say that in reversible process, the change of entropy is 0. That is, entropy remain constant or same in reversible process. Dear student, now we will see the change of entropy in an irreversible process. That is, you know what is irreversible process. Suppose we consider two body in a system. One body is denoted by A and another body is denoted by B, right? The temperature of body A is denoted by T1 and temperature of the body is denoted by T2. If T1 is greater than T2 and if the body are connected thermally, then a certain amount of heat will be converted or transferred from body A to body B because there is a change in temperature. If we consider the Q amount of heat will be converted from body A to body B, then in both case or in both bodies the change of heat will be take place. So change of entropy will be also changes consequently. If we calculate the change of entropy in case of body A, so we can write for body A, so change of entropy del S1 can be calculated as Q divided by T1, right? And we can express this by a negative sign because here heat is radiated or amount of heat is decreasing from the body A. So in that case the change of entropy will be negative, right? And on the other hand, the body B will absorb Q amount of heat. So the change of entropy for the body B, the change of entropy del S2 will be plus Q by T2 because the body B will absorb heat. So entropy of the body will be positive or increase. So total change of entropy in the system del S is equal to you can calculate Q by T2 plus minus Q by T1. Dear student, you know T1 is greater than T2. So from the expression we can say that the ratio Q by T2 will be greater than the ratio of Q by T1 because T1 is greater and T2 is less. You know, in case of fraction, if denominator, the fraction whose denominator is greater will be smaller. Here denominator is greater, so it will be smaller and this will be more. Therefore, we can say that here Q by T2 greater than Q by T1 since T1 is greater than T2. Therefore, del S is positive. That is, we can say that in irreversible process the entropy increases, right? Dear student, now we will see and very important topic for your comprehensive question or comprehension based question, and that is thermal or heat death of the universe. You know, we can perform work or we can get work using heat or the flow of heat. Again, in the universe most of the processes are irreversible, and you know in our previous discussion in irreversible process the entropy increases, right? That is, entropy increases means the disorderliness or entropy of a system increases, and after a certain period the disorderliness or entropy of a system will be maximum, right? And at that moment heat, the possibility of obtain work using heat or flow, by the flow of heat will be 0. Since the disorderliness will be maximum, then the possibility of obtain work will be minimum or 0, right? That is, the heat will not perform work anymore. So this situation of state or entropy is known as thermal death or heat death of the universe, right? I hope you got it. This is very important for your comprehensive question. Dear student, now we will see some important expression for the change of entropy, right? You know, when heat is applied to a system or heat is radiated from the system, then the change of entropy takes place, right? You know, for the change of entropy, we need to first consider the absorbed heat or applied heat to the system, right? When heat is applied to a system, there are two types of change will be observed. Sometimes the state of the matter will be changed due to the application of heat, and sometimes the temperature of the system will be changed, right? When the state of the temperature will be changed, then the temperature remains same, and in that case the entropy can be calculated as, you know, change of entropy can be expressed as del S. Del S is equal to del Q divided by T. Here del Q is the required heat to change the state of the matter, and this is the T is the temperature which is remain constant. As for example, when we convert ice to water from 0 degree ice to water at 0 degree, here the temperature remains same, because the temperature of the ice was at 0 degree and the temperature of the converted water also 0 degree, but the state of the matter changes from solid to liquid. So in that case the expression can be expressed as del S is equal to mLV divided by T, right? Here del Q can be expressed as mLV, sorry, mLF. That is LF is the latent heat of fusion. Again we can express del S is equal to mLV divided by T, right? When we convert the water at 100 degrees Celsius to vapor at 100 degrees Celsius, in that case the temperature also remain same at 100 degrees Celsius, but the state of the matter converted from liquid to gaseous state. So when the temperature remains same, then we can express the change of entropy like this expression. Okay, so these are the expression when temperature remain unchanged, right, dear student? But when the temperature changes, then the expression for the change of entropy will be del S is equal to ms ln T2 minus ln T1. That is, T1 and T2 are the temperature of the body. T1 is initial temperature of the system or body, and T2 is the final temperature of the body. So using this expression we can calculate the change of entropy when the temperature changes due to the application of heat. Right, dear student, I hope you got it. These are very two easy expression for our mathematical problem. Okay, now we are going to solve some mathematical problem, that is how can we calculate the change of entropy in different cases. Okay, dear student, here is our mathematical problem. In the problem they said that calculate the change of entropy when 5 kg ice at 0 degrees Celsius converted to water at 0 degrees Celsius, right? Here you can observe that the temperature remains same, that is the temperature of the ice was 0 degrees Celsius and the converted water was also 0 degrees Celsius. So temperature remains same in this sense, but the state of the matter was changed, right? So in that case, you know, the change of entropy can be calculated by del S is equal to del Q divided by T, because here the temperature remains same. Dear student, so we can calculate here the mass of ice five kg, okay, and the temperature T is equal to 0 degree Celsius, that is 273 Kelvin. And you know, to calculate the required heat, here we need to know the latent heat of fusion of ice, that is LF. Ice, which is denoted by LF. LF is equal to 336,000 joule per kg, right? So dear student, here the change of entropy del S is equal to del Q, that is required heat divided by temperature, right? Here del Q can be calculated mLF, that is required heat to change the ice to water, divided by T. Here m is equal to 5 kg, LF is equal to 336,000 divided by temperature 273, right? And the calculation, after the calculation you will get 6153 decimal 85, and the unit will be joule per Kelvin, right? So unit of heat is joule and temperature is Kelvin, so unit will be joule per Kelvin. Dear student, I hope you got it. Dear student, in our next question they said that 5 kg water at 0 degree Celsius converted to water at 100 degree Celsius. Here the temperature of the substance was changed from 0 degree to 100 degree, but the state of matter was same, water to water, right? So in that case we can calculate the change of entropy in this way. Here mass of the substance, mass m is equal to 5 kg, right? The temperature of the initial temperature of the substance was 0 degree Celsius. So initial temperature T1 is equal to 0 degree Celsius, that is 273 Kelvin. So final temperature T2 is equal to 100 degrees Celsius, that is 373 Kelvin. And in this case we need to know the specific heat of water to calculate the required heat to convert water 0 degree to 100 degree Celsius, right? So specific heat, which is denoted by S is equal to 4200 joule per kg per Kelvin, right? We know change of entropy del S is equal to, here in this case the change of entropy will be ms ln T2 minus ln T1, right? So using the value of m, 5 multiplied by 4200 multiplied by ln 373 minus ln 273, right? And after the calculation you will get 6554 decimal 24 joule per Kelvin, right? So dear student, this is the change of entropy in conversion water at 0 degree to water at 100 degree Celsius. Okay. In our next question, they said that calculate the change of entropy when 5 kg water at 100 degree Celsius converted to vapor at 100 degree Celsius. Here the temperature remains same 100 degree to 100 degree, but state of the matter converted from liquid to gaseous state. So in this case, mass m is equal to 5 kg. Dear student, you know, to calculate the required heat in this stage, you know, for the conversion of liquid to gaseous state, we know the value of the latent heat of vaporization, right? So latent heat of vaporization, which is denoted by LV. LV is equal to 2268000 joule per kg, right? And temperature T is equal to 100 degrees Celsius, that is 373 Kelvin. We know del S is equal to del Q divided by T, right? Here del Q will be M L V divided by T. So M is 5, L V means 2268000 divided by 373. Okay, and after the calculation you will get 3020402 decimal 24, right? And the unit will be joule per Kelvin. Okay, dear student, this is the change in entropy in the conversion of 5 kg water at 100 degree Celsius to vapor at 100 degree Celsius. In the last question, they said that calculate the change of entropy when 5 kg ice. Here the initial state of the matter was ice at 0 degree Celsius converted to vapor at 100 degree Celsius. That is, here the state and temperature both of the matter were changed. So dear student, you know, here the required heat to convert the ice to vapor at 100 degree Celsius can be calculated or need to be calculated in 3 steps, right? You know, when the state of the matter change, then temperature remains same. So that will be the first step, and in this step the calculated heat to be calculated by, or required heat to be calculated by using the expression of MLF. And in the second step, the water will be converted from 0 degree Celsius to 100 degree Celsius, that is which we have calculated in the question for the question of B. And finally we have to calculate the required heat to convert the water at 100 degree Celsius to vapor at 100 degree Celsius, and the respective change of entropy will be calculated in 3 steps, right? So we can say that change of entropy in changing ice to water at 0 degree Celsius, right? This can be calculated as del S1 already we have calculated the value in our previous calculation. It will be 6153.85 6153.85 joule per Kelvin, right? Then change of entropy in changing water at 0 degree Celsius to water at 100 degree Celsius, right? This change of entropy can be calculated or denoted by S2. You know, in our previous calculation we have got that 6554.24 6554.24 joule per Kelvin, right? And finally the change of entropy in changing water at 100 degree Celsius to vapor at 100 degree Celsius. This may be represented by del S3 and it will be 30402.24 joule per Kelvin, right? So dear student, to convert the 5 kg ice at 0 degree to vapor at 100 degree Celsius, so total change of entropy will be the sum of these three change of entropy. That is, therefore del S is equal to del S1 plus del S2 plus del S3, that is 6153.85 plus 6554.24 plus 30402.24 joule per Kelvin, and after the calculation you will get 43110.23 joule per Kelvin. Right, dear student, I hope you got it, and I hope this will be very helpful for your upcoming exam, right, dear student. But you need to practice this type of problem from your textbook. So thank you very much being with me in my class. May Allah bless all of you. Assalamu alaikum.